in this problem, first we will fix x. Let's take x to be any real number. We've taken x to be a. And what is a here? A is any real number. You can take it to be anything, 5, 6, 2, root 2 pi, anything. So we have fixed x. Fix x equals to a, and we take as a plus h. And you know what h is here? H is a very small number here. Well, it's not really a number as much a constant. So h is not 0, and we have taken x to be a and y to be a plus h. And of course we'll tend h to 0 in the solution. Now what will I do now is I will rewrite this inequality in this form. But I hope the question is clear here. We are to find all such functions. I have not mentioned here, I should have mentioned. Find all functions such that f belongs f takes a value from R, and the codomain is also R. Equality for all x and y belongs to R. We have to find all such functions, and so far we have come this far. And now I will divide this whole by x minus y modulus less than x minus y modulus square. And this inequality is true for all x and y. Now I'll replace the value of x as a and y to be a plus h. So I will have a minus, further I should have written it in this form, a plus h. I can switch this because it's modulus. The minus sign which will come out will be nullified by modulus, so I can write in this form, and this will become just h. And here I will have make the inequality on both the sides. Oh, sorry, limit on both sides. So now what we'll do is we'll take limit. Limit h tends to 0, function a plus h minus function a h modulus. And here it will 0, and we also know since this is modulus, it has to be greater than equal to 0. Now you see we've got this limit between 0 and 0, and you know how we got 0 here. If we have taken limit h tends to 0 h square, it would be 0. Okay, so this limit exists very easily and it is equal to 0. It's very clear. But through that, what we have also done is we have also proved that this limit exists. And the reason why it exists is this limit can only be one number now. It has to be 0. And that's how we have showed that this limit exists. See, it so turns out that we were also able to find the value of the limit. It's beneficial, of course, it's very beneficial, but our first concern was to show that the limit do exist. And this is how we showed, because this limit is between two numbers, 0 and 0, so this limit has to be 0. And if we have shown some limit is equal to 1, then the limit exists. So this limit exists. and we know this limit is a very definition of the derivative, so we've got f dash a is equal to 0. This is a and this is 0. And if you focus here, we have to see we have taken fixed x as a. A is any real number, as I've told you earlier, 2, 3, 4, 5. But this is arbitrary. We have not fixed a to be any particular. See, we could have taken a to be. Suppose in this procedure we had taken a to be 5. So it's true for 5. F dash 5 is 0. Suppose if we had taken for 6. So it's true for 6 as well. So in a nutshell, since a was arbitrary, we could say that f dash x is 0 for all x belonging to R. So this is what we have proved, and from here on it's very easy to imply that f is constant function. So that's how we have found all the functions such that which satisfy this condition. We could not have importance of being able to show that this limit exists is very essential, and you will see how. I will show you. I will give you one more example where it isn't very obvious upfront that the limit do exist, and you see that in the next example that we are going to do now. This is our next example. You can read out the problem. It's very similar. We have to find all such functions which satisfies this condition for all x and y belongs to real numbers. And here you will see how vital it is to be able to show that the limit do exist before we use the symbol f dash x. You cannot just write f dash x equals to something before you have shown the limit does exist. Okay, this may look very easy to some folks out there, but it isn't. It's kind of tricky problem, deceptive one. You see, what most students would have done is, this is what they would have done. They would have, fixed x. First, what they'll do is they'll fix x equals to a belongs to real number, and they then might have taken y to be a plus h. Okay, no problem. Then what they would have done is a plus h minus a divided by, they would bring this thing down, x minus y, and x minus y would become just h. You would have this. It's easy to see how I have using this. I've got this. I've just substituted the value of x and y. Okay, and now what they'll do is they'll take the limit. So if we take limit h tends to 0, and if we take limit here, limit h tends to 0 to, it will remain 2. Many of the folks out there would say that the limit is equals to 2, but that is wrong. The limit can either be 2 or it can also be minus 2. So there's ambiguity whether limit is 2 or minus 2. So the next step itself is wrong. From here on, I cannot say this. I cannot use this symbol. Using this symbol itself is a wrong step. Also, from here on, this isn't very beneficial. It is beneficial to some extent, but it's not very beneficial. This deduction, this what we have got. But even this is wrong. We cannot use f dash a. The reason why we cannot use this is, for this symbol to make sense, this limit have to exist. And you know, limit can only take one value, but this sentence line says the limit can take two values, either 2 or -2. So you know, this limit has no one particular specified value. So this limit, right now we cannot say from this that the limit exists, and therefore we cannot use this symbol. And if you so that's wrong. But if we just for the sake of explanation, if we take this symbol from this, we can imply that f dash a is either 2 or -2. So f dash x is either 2 or -2. This is what most students would have done, and then they would have concluded then that fx is 2x plus c, and the other solution is fx equals to -2x plus c. But that is wrong. You cannot say that the function is 2x plus c throughout, like it's like this. So you can say, you know, what you cannot say is these two are all the functions. Of course this function will satisfy these conditions, very well true, but you cannot say that these two are the only two functions, at least from this calculation. Why? Because what we have got is f dash x could be 2 or -2 at each value of x. So one function could be this. So at each point, derivative at this point is 2, here -2, 2, -2, 2. And derivative at this point do not even exist, because at this point it can either be 2, and you know why it is not there does not exist here, because at this point we can draw two tangents. One tangent would be this and the other one would be this. This would have slope -2, this would have slope 2. So the derivative, there's ambiguity what derivative is. So that's what this through this much of calculation, what we've got is this. We can from here deduce that f dash x is equals to 2 or -2. 2 for some values of x and -2 for some values of x. That's what we have got. But this isn't much helpful. There are infinitely many functions which satisfy this. I've given you one such example, or you can construct one more example. You have seen one function, this is the derivatives throughout a 2. You have got one more function where the derivative changes the value. It's 2 here, -2, 2, -2. Or you can have a function which is a derivative just -2, a straight line. Or what you could have is a function this -2 here, then it can do this and then it go up. This function will also satisfy this condition. So this calculation isn't much helpful, because this isn't telling us, this is telling us that there are many such functions, but which is not true. There are only two such functions which satisfy this entire condition. How can I say that? I will show you in a while. So you see using this symbol itself is a wrong thing. You cannot do that because you have not shown that the limit exists. That's why I was stressing so much in the previous example here, that here we were able to show that the limit exists and it is indeed equal to 0. There's no ambiguity. It is indeed equal to 0. There's no ambiguity here. The limit is equal to one specific number, unique number, which is 0. So when a limit is equal to one unique number, then the limit exists. Here we can't say that. Limit can have two values, 2, -2. So limit we cannot imply from this that the limit exists. So what can we do in this example now? How to solve this problem? So that's what I will do here. So this is a solution, how the solution would go. First I'll fix x equals to a, and then I tend y to a. So I would have fy minus a from the equation we had, 2y minus a, and now I'll take the limit y is tending to a. So I'll have limit y tending to a, this, and if I take limit on this side, limit y tending to a to y minus a, and I know this will become 0, so it is 0, and I know that this modulus is greater than equal to 0, so limit is squeezed between two zeros, so the limit does exist and it has to be 0. So this implies the limit exists, and the limit y tending to a function at y minus function at a is 0, and I have limit y tending to a f of y equals to f of a. What this tells us is that the function is continuous at a. That's the definition, very definition of continuity. Function is continuous at x equals to a, and since a was arbitrary, function is throughout continuous. The function is continuous for all x, since my a was arbitrary. So yes, so from this much calculation I have shown that my function is continuous. That's the first thing that we have managed to prove, that from the condition that would give us to us in the problem, which was this, from this condition that my function is continuous. Okay, now what will I do? I'll try to show my function is also monotone. Okay, so to show monotonicity, what I'll take is say fx is equals to fy for some particular x naught y naught, fixed x naught y naught, and then from the condition I would have that function x naught minus function y naught is equal to 2 times x naught minus y naught. So since these two values are equal, so they are equal to 0, then it will imply 2 x naught minus y naught is 0, and this implies x naught is equal to y naught. Right. So this would imply that my function is 1 1. But you see, continuity, function is continuous and my function is 1 1. If we combine these two, we can say that my function is monotone. Combining continuity and 1 1ness, it implies the function is monotone. And it's very easy to see, if I have my function, it's continuous, it's 1 1, so either it has to go like this, it cannot come down, but if it comes down even a bit, then these two values are repeated, so it's not 1 1. So either it's always increasing and or it's always decreasing. So from that we've got monotonicity, and my function is monotone. either increasing or decreasing. Actually strictly increasing or strictly decreasing. Now, so there's only two conditions: either the function is continuously strictly monotone or strictly decreasing, strictly increasing or strictly decreasing. So that rules out all the possibility of functions that we were getting in the early solution of the function. So that's what it has done. It has ruled out all the other possible solutions, all the possible functions. This is not possible for that given uh, equality condition. So we only have two candidates now. Either the function is increasing or it's decreasing. I'm not saying it's linear. I'm not saying it's linear at all. We'll see now, and we will now linear. How? You can just you have to follow me here. So we'll take case 1. That the function is increasing. So in this case, what we do, we take y greater than x, both belonging to real numbers, and we have y minus yx equals to 2. And you see, this was the condition, but now since function is increasing, this would imply f of y is greater than f of x, strictly greater than that. So I can remove the modular signs. So I would have this, then I can divide by y minus x, and this is equal to 2. And now I can take the limit. I can fix x. Now the limit would exist, and I would be able to show that the derivative does exist and it's equal to 2. So fix x equals to a belonging to r, take y to be a plus h. Then I can rewrite, I can substitute these values in this, and I will get f a plus h minus f of a divided by h equals to 2. And now I'll take the limit. I'll write the limit right here. H tends to 0. This 2 will remain just 2. And now this equality tells us that the limit is equals to 2. There's no ambiguity here, and it does tell us that the limit do exist, and therefore writing this makes sense. This notation makes sense. And since a is arbitrary, I would have f dash x is equal to 2 for all x belonging to r, and it would imply my function is 2x plus c. So I've got one solution, one candidate, or not just a function which have passed the condition, or is the solution. In case 1, if function is increasing, I've got this as one function, and in case 2, the function is decreasing, I would have f dash x equals to minus 2. From there I will have my function to be minus 2x plus c. This is very straightforward, very case 1. So you can do it yourself. And that's it. The problem is solved. I've been able to show now that this is one function and this is the second function. There do not exist any other functions in that equality. So the problem is done.